So let's suppose that several objects roll without slipping along a frictionless inclined plane that has a height of h. Now, if each object has identical mass and begins and ends at the same exact position along our inclined plane, we want to answer the following question. Which object reaches the ground first? In other words, which object has the highest linear velocity at the bottom of the inclined plane? So let's begin by listing all the types of objects that we will be testing. So we have a thin loop, a solid cylinder, a solid sphere, and a box. Each one of these objects has the same exact identical mass and begins and ends at the same exact location. So each one of these objects begin at a height of h above the ground, and each one of these begins with initial velocity of 0. So we basically have to recall that because we have no friction in our system, that means we have a conservation of mechanical energy. So all the gravitational and kinetic energy at the beginning is equal to all, or the sum, of the gravitational potential energy at the end. Now initially our objects are not moving with any velocity, so that means initially we only have gravitational potential energy. Now at the end, when the objects reach the ground, all the gravitational potential energy has been transformed into kinetic energies. And there are two types of kinetic energies that we must consider: rotational kinetic energies as well as translational kinetic energies. So basically in the beginning we have gravitational potential energy, and at the end all of that energy, due to the gravitational pull of the earth, has been transformed into kinetic energy. So let's put that down on the board. Let's put that into equation form. So before the objects begin rolling, we have mgh. After our objects begin rolling, we have the rotational kinetic energy plus the translational kinetic energy. So rotational is given by 1/2 ICM omega squared, where omega is the angular velocity of the object and ICM is the moment of inertia of our object about the center of mass. And m VCM squared, where m is simply the mass of the object and VCM is simply the linear velocity of the object at the point of the center of mass. So basically we have to recall that angular velocity of an object is equal to the linear velocity of the object divided by the radius of that object. So we replace our omega with VCM divided by r. And because it's squared, we obtain VCM squared divided by r squared. Now notice we can rearrange this equation in the following way. Because we have VCM and VCM that appear on both of these terms, we can break that term out and we get the following result. And now we can solve for the velocity at the bottom of our inclined plane, and we get the velocity is equal to the square root of mgh divided by this entire term, because we bring it over to the left side. So we get mgh divided by our moment about the center of mass divided by 2r squared plus m divided by 2. And the whole thing is square rooted. So now we have to use this equation to calculate what the final velocity of each object is at the bottom. Now notice the box has no moment of inertia, and that's because when the box is sliding without slipping, it's not rotating. So all of that gravitational potential energy goes into kinetic energy of its translational motion. So the box will have the highest value for VCM, and the box will end up at the bottom first before any of these other objects. Now let's consider objects 1, 2, and 3, beginning with object 1. So we basically want to plug in our rotational momentum of the object I into this equation. So that's exactly what we do in part 1. The velocity of the object about the center of mass at the bottom of the thin loop is equal to the square root of mgh divided by, so the I is replaced with mr squared, and we divide that by 2r squared and add plus m divided by 2. So notice m's appear in each term, so the m's cancel, the r squared cancel, and we get the following result. The bottom adds up to 1, so we simply get the square root of g multiplied by h. Now, if we follow the same exact procedure for object 2 and object 3, we get the following two results. Now, notice the lowest velocity of an object is of object number 1. It has square root gh. This has the second lowest value, and this has the third lowest value. So this object reaches the bottom before object 2 and object 1, because at the bottom it has the highest velocity, because we're dividing by a smaller number than this number and by a smaller number than this number, because here we're dividing by 1. So that means the box will reach the bottom first because it will have the highest velocity at the bottom, because all of that gravitational potential energy has been converted into kinetic energy due to its translational motion, because the object is not rotating. But for these three cases, a bit of that gravitational potential energy has not only gone into kinetic energy of its translational motion, but also into its rotational kinetic energy. And object number 1 will reach the bottom last because a greater portion of its gravitational potential energy has gone into increasing its rotational potential energy as compared to objects number 2 and objects number 3.